Hi guys, here's my solution to question 9.57. So in this question, the Harvard College Alcohol Study interviewed an SRS of 14,941 college students about their drinking habits. Suppose that half of all college students, quote, drink to get drunk at least once in a while. So that is, let's assume that the truth is that P equals 0.5. That is the percentage of college students that actually exhibit this particular behavior. So in part A, what are the mean and standard deviation for the sample proportion of college students who drink to get drunk? So the mean, or the center of our distribution of p hats, will be the true value of p that we're assuming is 0.5. That's what we will use then to calculate the standard deviation for our distribution of p hat. That will be the square root of p times 1 minus p. Of course, in this case, those are the same, divided by the square root of our very large sample size. So we have a very small standard deviation of 0.004. Of course, that's all the question really asked you to do, but I think it's important to remember, not just in terms of the center and the spread, but this distribution has a shape. Our p hats would be distributed normally with this center, there's the mean, and with this spread, there's the standard deviation, but under two conditions here. The independence condition tells us that 10 times this very large sample size, that would be 149,410. That should be less than or equal to the population of all college students, and that's true. The normality condition here, we would take our, again, very large sample size times p and our large sample size times 1 minus p. Of course, in this case, both of those are the same. So we get very, very large expected counts of success and failure here. Both of those are greater than or equal to 10 with no problem. So both the independence and normality conditions are satisfied. So this is the sampling distribution for p hat that we can use to calculate the probability in part B. This says to use the normal approximation to find the probability that a sample proportion would end up between 0.49 and 0.51. Of course, all of this is based on the assumption that the truth in this population is that half of the college students in the population actually exhibit this behavior. Everything is based on that assumption. So again, the normal approximation simply means that our normality condition is satisfied, so we can use the normal distribution to help us here. And the easiest thing to do is to change our p hat straight into z-scores. So the lower boundary is going to be the 0.49, but what you can see here is I've taken away the mean, 0.5, and I've divided by the standard deviation of 0.004. That will give us a lower z-score. And then the 0.51, I've taken again away the mean and divided by the standard deviation, so that will give us an upper boundary, an upper z-score to use in order to calculate this probability. So if we go to the calculator, this shouldn't be particularly hard to do. So here is the 0.49, take away the mean, and we'll divide by our really small standard deviation of 0.004. That should be negative 2.5, and it is. So similarly, the 0.51 is to the same extreme on the right. I don't really need to do this. I'll do it anyway. It makes you feel better. There's the 0.51. Take away the mean of 0.5 and divide by the standard deviation of 0.004. So that should give you a positive 2.5. So those are the z-scores that bound this probability on the left and on the right. So we really want the probability that our z-scores are between negative 2.5 and positive 2.5. So I would advise you to do that with the normal CDF command. Again, I think it's a good idea to have a picture of what's going on here. So I'm going to go ahead and draw this picture in terms of z-scores. So that means that when I draw my normal density function, I want to label my center at 0. Z-scores have a mean of 0. Here is my standard deviation of 1 for my z-scores. So I want to go all the way up here to, let's call it 2.5 is my upper boundary. And I have a lower boundary of a z-score of negative 2.5. So this question asks me to find the probability in between these two boundaries. So I'm finding the area under the normal density function between negative 2.5 and positive 2.5 between those z-scores. This is most easily done using the normal CDF command. So I would go to second variables. Normal CDF is the second option. So my lower boundary is negative 2.5. The upper boundary is positive 2.5. And this should give us, of course, a very large probability, a large likelihood. That's what we would expect. So let's call it 0.988. And this shouldn't be much of a surprise. So indeed, if indeed the truth is at 0.5, then with such a large sample size, there is very little variability here in my p-hats. So indeed, I would expect to be very close to the, quote, truth that we have assumed here at 0.5. So it shouldn't be a surprise that my p-hats between 0.49 and 0.51, that is very likely because indeed my p-hats should be in close to the value that we have assumed is true, that is at 0.5. And again here between those two z-scores, our likelihood is 0.988. That's what we should expect given how small our standard deviation is, and that is in truth because we have such a large sample size. We don't expect a lot of variability from the, quote, truth, which we have in the middle of our distribution here. Hope this has been helpful.